So when we did the lesson for 7.5 part 1, we looked at higher order derivatives like a second derivative, third derivative. This section is going to tell you how those things relate to like the real life application of things. So what we're looking here, and this would be most closely related to physics. So if you took physics or are in physics, this would be the best connection to that class as far as what we do. And so what we're looking at here is if you take the initial function that you would start with. If we're talking about an object, we would use that to describe its position. And so we refer to the original function as the position function or the displacement function, same thing. But this would describe the derivative of the displacement function with respect to time. And so what happens over a course of time as something changes position, you get its velocity. So velocity is the derivative of displacement. So if displacement function tells you the distance that something travels, velocity would tell you the rate of change at which it travels that distance. And so that's what we get for velocity is going to be the derivative of the position function. So if you look at this example right here, so if we're talking about displacement given by this function right here, where t is time in seconds, if they just said, what is the displacement at 2 seconds? Well, I just plug 2 into the displacement function right here for t and there. And so we can say, well, this is how far it traveled over the course of 2 seconds. But when they ask for the velocity, now they want to know how fast did it travel, or what was the rate of change that it traveled in 2 seconds of time. And so for velocity, if we take the derivative of our displacement function, so if we take the derivative of this, so you can see right here that the derivative of the position function is velocity. So to get velocity, if we do the derivative of our position function, we get 4t plus 5. So that would just be using the power rule to get that. So we have our rate of change, which is velocity. And so now if I wanted to know the same information at 2 seconds, if I sub a 2 into my velocity function, so 4 times 2 plus 5, that should say 5, is going to give you 13 meters per second. So remember, when you do rate of change, which velocity is the rate of change of position, you're always comparing something like y minus y over x minus x. So that's why for position, all you had was meters, but when you do velocity, you get something compared to something else. So this is distance compared to time, or we would see that as meters per second. And that's where the velocity comes from. So looking down right here, again, one more example. I would encourage you to give part B a try. Right here, it's just like the one I just did. But similar question, if this is the position function or the distance function that we have right here, if we said what is the displacement or how far did it travel in 4 seconds? So if I plug a 4 in for t into my position function, we're going to see that this thing traveled 77 meters over the course of 4 seconds. And then if I wanted to know its velocity, so now we're talking about the average rate of change over those 77 meters. And so if we take the derivative of our position function, so using our power rule, if we do the derivative of that function, we come out with our velocity function, which is this one. So now if we want to know the velocity at 4 seconds, we can just plug in a 4 in for this t and see that we traveled over the course of that distance, we traveled at a rate of 50 meters per second. For part C, this is the same concept, but you got to take note of the wording on this one. So this one says now find the time. So now we're looking for a t value when the particle is at rest. Well, when something is at rest, that means that it has a velocity of 0. And so it takes a little interpretation of what this would mean. But if it's resting, then it has 0 velocity. And so if my velocity function of this one, so you can see here's the original. So if I find the velocity function by taking the derivative of this, I get this velocity function here. Since the particle is at rest, I would set this equal to 0, like you're seeing right here, velocity equals 0. And if I solve for time, I can see that that happened at 2 seconds. So now for the second part, when they say find the displacement when the particle is at rest, well, I know that occurred at 2 seconds. So if I go to my displacement function and sub in a 2 for time, I can see the distance that we were at, or the displacement that it was at 2 seconds, and that's where it would have been at rest. So moving on down here to acceleration, remember this is linked to what we did in our last lesson on higher order derivatives. Well, that's what we're getting into here with acceleration. When it comes to displacement and velocity, acceleration is the next level down. So if the displacement is the original function and velocity is the first derivative, acceleration is the second derivative. So acceleration is the rate of change of velocity. And so that's what you're getting here with the acceleration. Acceleration is the derivative of the velocity, and that's what you're getting right here. So the other way to look at that is the acceleration is the second derivative of the displacement function. So if you look at this one that you're seeing right here, so for this part C, where you got the 5t to the third minus 2t squared, it's going to kind of ask you all. So this is a good question, so you can see it all put together. So the displacement at 3 seconds. So remember, displacement's the original function. That's our position function. So if I just sub in a 3 for time, I can see the distance that was traveled over 3 seconds. If I want to know the velocity, so the rate of change of displacement, so velocity is the rate of change of position. So if I did the derivative, the first derivative of position, I'm going to get this function right here. So now if I sub in a 3 for time, so now if you sub that in, you can see that we come out with a rate of change of 123 meters per second. So for the third part of this, for acceleration, now they're asking for the rate of change of velocity. So if I do another derivative and get right down to here, 30t minus 4, and you can see this is the derivative of velocity, which is also to say this is the second derivative of our position function that we started with. So we did a second derivative of this, and now if I sub in a 3 for that one, now I'm down to meters per second squared. So notice the rate of change of the rate of change kind of adds in that extra element, and so this is how fast you are changing velocity at this value here. So again, just for these last two, just a matter of getting comfortable with the wording of the question. So in this one here, you got to notice that they are asking for displacement when a velocity is 35. So this right off the bat tells me I need to identify the velocity function, set it equal to 35 so I can solve for time. And so if I take the velocity function that we have right here, so this was our velocity function, if I set this equal to 35, I can solve for time. So we are solving a quadratic here, so you could do this by factoring. You could do it with quadratic formula. Any of those are fine. For this one, you do get two answers, so I'm going to get a positive 5 over 3 for this one, but I'm going to get a negative 7 for this one, and here's where some logic has to come into play. Time can't be negative. I can't have a negative amount of time, so I'm going to throw out the negative 7, and I'm just going to use 5 over 3. To answer this question, they were asking about displacement, so now that I know the time, I can take 5/3 and plug it into the original position function in order to figure out the distance that was traveled at that amount of time. So last one here, similar idea, but now we're starting with acceleration. So this one would tell me to get the second derivative of displacement, which is acceleration. So if you look at this one right here, I'm going to set this acceleration equal to 56 and solve for time. So here we are setting that equal to 56. That tells you that time was 2 seconds. Since this one is asking for displacement, I'm going to take that value of 2 and plug it into my position function to figure out the distance traveled or displacement at 2 seconds. And so that's where we get that 32 meters from.